Hello, everyone. My name is Igor Masyagin, and I'll be an expert for the next talk. The next talk will be given by Itai. Itai is a developer or team lead, actually, in research and development department in a company called Treeverse, and he's going to talk about lakeFS, which is an open source tool that's supposed to give you very nice Git-like experience for your data. So, Itai, how are you feeling? Is everything fine?
Feeling pretty good.
Yeah.
Yes, it is.
We're excited to hear about your talk. Anything you want to add before start?
No, just that I'm excited to be here and thank you for inviting me.
Thanks.
And that's it.
Yep.
Okay, so let's start with the presentation.
Let's go.
So hello, everyone. Today we're going to talk about creating a Git-like experience for your data lake analytics. So, a little bit about myself. I'm an R&D team lead at Presto, which is the company behind the open source project lakeFS, and I come from Tel Aviv in Israel. The agenda for today, we're going to discuss data lakes and the challenges you have when you're managing your data in the data lake. We're also going to learn how you're going to make your data lake more reliable using lakeFS. And I also hope that you will be able to see a quick demo about how easy it is to use lakeFS. So data lake architecture. The whole premise of a data lake is that I have this one place, one centralized repository inside my organization where all data sources can write to and all query and processing engine can read from or do queries at. And everyone speaks the same language. For instance, I can write files to S3 and read them later on. I can spill Parquet files from my Kafka topic to the lake and read them with Spark or with some Presto query. And all of this works because the lowest common denominator is just flat files and S3. Now, it's a great architecture with great application ecosystem. It allows me to store tons of data at an affordable cost, and I get very high throughput. And it all sounds pretty ideal, except that in reality, there are some challenges. It creates quite a few problems because now you have this one big place, which is like a huge repository, which is actually a huge shared folder. Now, it's a shared folder where all your objects are stored together. And this shared folder becomes really hard to manage. If you think about the challenges in managing the data lake, you can notice that it's quite similar to the challenges you have when you're managing a shared code repository. With both the data and the code repositories, you need to have the ability to test and try your changes in isolation while you do no harm to your code or data in production. You would also probably like to control whatever gets into the repository and the quality of the changes you introduce. So if the challenges between code and data are similar, and we have the best practices when we are managing code, why don't have the same practices for data? In a perfect world, one would manage his data from development to production in the same way you manage your code. Now, this is exactly why we've built lakeFS, and this is to help you manage the data the way you manage code. If I had to explain what lakeFS is in one sentence, I would just describe lakeFS as an open source atomic version data lake on top of your object store. What lakeFS does is to power your object store with capabilities that we believe are missing from an object store. Missing from an object store in a perspective that makes it a good data lake. And those missing capabilities are basically mostly around versioning of the data. The idea of lakeFS is to provide a layer that sits somewhere between the object store itself and the tools that you use in your organization and act as a layer of manageability and reliability. So let's quickly describe how this works. It is API compatible. It means that we expose an API which is a superset of the S3 API. So if you have an existing application that knows how to communicate with S3, you can also communicate with lakeFS in the exact same manner. It is transparent to your application. For example, if I have a Spark job that reads and writes from S3 directly, all you have to do is just changing the endpoint from S3 to your lakeFS installation and keep working as usual. lakeFS does all the magic between your client and the object store. The versioning engine is what gives you the Git semantics. Now, our API is compatible with S3, but we need more than that in order to have the versioning semantics and capabilities. And that's the part that is missing in our view from the current object store. And this is the additional API that we added to lakeFS. lakeFS makes S3 behave like a giant Git repository. I can now create branches, do commits. I could diff between the commits I just created. I could merge commits, and I could also roll back to a commit, which represents a point in time. I can also time travel between commits and view different versions of the data inside my lake. In short, all the powerful primitives that Git provides are now available on top of my data lake. Now, although lakeFS lets you manage data the way you manage code, you need to know that code and data are somewhat different, especially when it comes to the scale. Our goal is to give you the git-like experience, but having it scale to multiple petabytes of data and potentially billions of objects. And doing that by being as transparent as possible. We want you to be able to do everything like you did before, like running your Spark jobs, your data streams, but we want to have the Git capabilities on top of the existing lake. Now, the only change you would see is that you would need to interact with lakeFS in a context of a branch, as you would probably do when you interact with your code repositories in Git. If up until now you would communicate directly with your object store by specifying some file bucket and a path, now lakeFS will have you prefix the name of the branch you would like to point to. And your application suddenly becomes branch aware. The concept of branch awareness also extends to the Hive metastore that many people are using to decouple storage and schema. If I have a table that was linked to a set of files hosted on a certain branch, I can create a clone, and this table will then exist for another branch that I'm using. Now, this would work with any application that's currently communicating with the object store, and you could do the same trick to integrate with any S3 compatible tool your data stack has. You will need to set the S3 endpoint to your lakeFS installation and have your coil point to the branch of your lake. Now, let's see where lakeFS data versioning capabilities can help you overcome your challenges when managing data lakes. The easiest place to start is playing with lakeFS in your development environment. This is something that is really a struggle for organization that we talked to before. Now, how do organizations try to achieve development mode today? They create an isolated staging repository. In order to create some isolated repository, organizations typically hack the way using one of two options. They copy their entire lake and create another parallel universe where everything works in isolation, but this is really expensive and also hard to maintain. They also sometimes copy just a sample of the data, and this is, again, hard to maintain, but typically it's not frequently updated, and therefore it is lagging behind production. And what they end up doing is not trusting this environment enough and not treating it as a real staging environment. When you're using something like Git that offers you all those isolation guarantees on top of the real production data, which runs in the same scale and characteristics, now that's a very powerful guarantee. Now you could trust your dev environment without paying the cost of copying data and without having to manage it yourself. With lakeFS, you could now experiment very easily. You don't need to copy data around anymore, because once you created your own branch, you know that it's frozen in time until you decide to update it, which you'll probably do by merging the master branch back into your branch. You also work in isolation. You know that no one else is going to be touching your data, and on the other hand, none of your changes are going to affect the production view or the main branch. Creating a branch in lakeFS is a very cheap operation, and you could decide to create new branch for any version of the experiments you're currently doing. Maybe you are tuning a parameter on each branch. Maybe you're even trying a different algorithm on a branch, or you just want to change part of your infrastructure where, for example, you want to switch to a different version of Spark. You can do all of these changes in isolation, and then because of the way that lakeFS works, these branches are available at any point in time. You can then simply change the branch prefix in the code that interact with lakeFS and get different results on each one of those branches. You could then continue with your experiments and read the results from each one of those branches for every change that you introduce. And then you could compare the results by diffing them, or you could test how jobs were affected by the changes that you did to a branch by simply pointing them to the branch that you want to test. Having all the results live in parallel on different branches and being able to work with different branches in parallel is maybe one of the biggest differences between lakeFS and Git. When you're using Git, you normally clone the repository and work locally while making the changes you perform to a single braid to a single branch at a time. In lakeFS, you could address whatever branch I want, but doing this at any point in time because all the branches live remotely. In this example, we have two experiments running in parallel and then using Spark for some aggregation. You could end the experiment by comparing the results of the two branches and basically decide which one you want. Now, the same thing works with any other framework. This is some example that is using Presto. It's doing the same thing as it would do directly with S3, but it creates an external table that points to an external location, which is mapped to a lakeFS branch named main. Now, main is the branch name and the path to where this collection lives. And from there, we can just use SQL on top of Presto to query the data within that branch. Okay, deployment. Now we are moving down the data lifecycle management path. During deployment, this is where you really start to benefit from having this tool in place. Every day we introduce new data to the lake, and even if the code and infra doesn't change, the data might. And those changes introduce potential quality issues. For example, if I'm using some client that sends me website events and there is a bug in that client, some error data may get into my lake and not as a result of the change that I did. And this is one of the biggest complexities of data products. The data we consume, it changes very frequently. What lakeFS does to mitigate that is enable you to create CI/CD workflows to help you validate the expectations and assumptions about the data before it goes live to production. You could now safely make changes to your data by ingesting new data in isolation and run validations before merging the data to production. You can also enforce best practices like defining the valid formats on the lake and making sure that breaking schema changes are not merged back into your lake, your main branch in the lake. And you could also test statistical properties of the data in order to avoid cascading quality issues. Now, if you think about it, it is similar to the data verification we would want to have for code. So how does this work? This is pretty similar to the way we today work with Git or GitHub. Working on my own branch, then when I want other people to be able to see the changes that I'm introducing, I do this by simply merging my branch into master or main branch. And lakeFS has the concept of what we call pre-commit and pre-merge hooks, that those will allow you to define a set of actions that should pass when you are trying to commit or merge something. Now, the most common use case for this would be to set some ground rules for what formats get into the main branch. In this example, I'm making some changes in my branch, and as part of the change, I'm introducing a few Parquet files, which I'm okay with, but I'm also introducing a new CSV file, which I don't want in my lake because it costs more to store something not in a Parquet format, for example. Now, I can prevent this change from ever reaching my production branch by using the lakeFS hooks. I can define a hook that will run before every merge operation that says that CSV files are not allowed in my lake. The hook will fail when I try to merge my branch into main, and the merge will be blocked. Now, this all sounds pretty trivial, but if you think about all of this from the data consumer side, it is a very powerful guarantee. As the data consumer, I am now assured that if I'm reading from the main branch, I'm always going to see the set of specific formats that are allowed, or some specific schema that is allowed. And that all depends on the hooks I've configured. Using hooks, I can do all of these very safely. Now, the demo code in this example is used to validate columns in our Parquet files. We used here PyArrow, which is a Python library that integrates into the Arrow ecosystem. And we used it here to do a trivial operation. We're reading the Parquet file schema and validating that the columns it contains, or it shouldn't contain any PII data. Now, in this example, I'll start by doing a diff that shows me the changes that are being introduced. I'm looking only for Parquet files. So for each Parquet files, I'm going to read the metadata and check what column it contains. If it contains, let's say, a user ID column, I'm going to raise a validation error and block the merge or the commit from happening. It means that I don't want to see any Parquet files with user ID column written to production environment because it's not allowed. Why is that? It's simply because I don't want any PII data on the prefix I'm currently working on, and maybe that prefix is public. Now, with 5 lines of Python, I can create a policy for my data lake that without lakeFS, it would be pretty hard to validate. I can implement my own business logic and define any rule that makes sense to my organization, and the timing for enforcing that rule is also up to me. Like if I want to do it before or after a commit or a merge. Now, comparing to code, anything from linting to testing of the data can be tested with the lakeFS hooks. Now, streaming requires some special handling, since you may say that every point in time is the same because data never stops arriving to the lake. With lakeFS, you can write the events to a side branch and commit to the main branch and merge the main branch whenever you like. It could be every 5, 10, 60 minutes. It depends on your use case. If you set the Kafka stream information, right here in the example, the topic and the offset in the commit metadata, you can later use it when you try to check the stream at a specific time. After committing to that special ingestion branch, and you can now merge it to the main branch, and this is when you want your hooks to run and validate the ingestion data. No, and the last use case is the production. And production, which is probably the most crucial part, errors sometimes occur. And when this happens, the best thing you can do is recover from it as fast as you can. You can now roll back the changes that were done to your data lake using the lakeFS revert operation. You can also troubleshoot production errors more reliably by using the snapshots of the actual data at the time of the error, and you can also get cross-collection consistency between different collections inside your lake. Reproducing a bug. So you upgraded Spark and deployed changes in production, and a few days later, you identified a data quality issue or a performance degradation or some increase to your info costs. Sometimes that requires investigation, which may take some time, and fixing. Now, lakeFS allows you to open a branch of your lake from specific merge or commit that introduce the changes to production. And using the metadata that was saved on the merge or commit, you can reproduce all aspects of the environment and reproduce the issue on that side branch and debug it. And meanwhile, you could revert the main branch to a previous point in time when you know it was safe, or you could keep it as is. It all depends on your users. So some use cases recap. We talked about the development environment, and this is where you want to safely experiment with the data without interfering with consumers in production that are reading that data. We also talked about deployment and during deployment, where you want to avoid any cascading data quality issues, and in production where you want error resolution and you want to quickly recover from failures and identifying the root cause, and by such basically decreasing the costs of mistakes that were made. Now, let's talk briefly about lakeFS architecture. And if you want, you can read more about our architecture and data models in our docs, which I'll share with you after the talk. lakeFS is not Git. The scale factor is completely different. We are talking about potential of billions of objects, and the velocity of changes that are happening to a data repository is much higher. If I have some automated processes or some dog making changes to my lake, I'm potentially reaching millions of commits per day. And the changes are not in the granularity of a line, but they are mostly at the object level. This basically means that lakeFS should be built differently from Git. It exposes similar API, but it works differently. The way it works is that lakeFS exposes what we call the S3 gateway, and this is what my application is communicating with. And as I mentioned earlier, this is transparent to the application. The S3 gateway speaks with what we call the metadata manager, that it handles all the commits behind the scenes. And these commits, while they look like Git commits, their data model is different. So the data model. Each commit of lakeFS is kind of a flat tree, which is composed of what we call ranges. And each range contains an ordered set of key and value pairs, where the key is the lakeFS stuff of the object, and the value is the object metadata, which includes a pointer to the object location and inside my S3 bucket and other or any other location where the data resides. On top of each range, I have a meta range which collects a set of ranges to compose a single commit. So every time I create a new commit, what I'm actually doing is to create new meta range that points to the most. It points to most of the same ranges my previous commit pointed to, but except for the ranges inside my meta range that were containing the change that I introduced to the objects. Therefore, creating a commit is not very expensive. All lakeFS have to do is to create a new range file and a meta range file that will represent the commit. And that represents a snapshot of the entire data lake at this specific point in time for that branch. This explains why creating a new branch is a cheap operation. All I have to do here is to create a pointer to an existing commit, which is the head of the branch I'm creating my branch from, the source branch. Now, our docs explains all of this data model in more depth if someone is interested in further reading. Okay, so let's see the demo. So I have a running lakeFS environment, which is running on AWS, and I've also created the first repository, which is the Smart Data repository. I'm also having the lakectl, which is the CLI tool that helps you interact with lakeFS. Now, right here, I've listed the repositories that I have, and turns out I have the Smart Data repository, the demo repository. I also have a notebook, the Databricks notebook that is going to simulate the Spark run. So let's see what we are trying to achieve here. I've created a new Spark session, and I'm pointing Spark using the credentials to the new lakeFS installation that I'm running. So all I have to do is set the three configuration, the access key, the secret key, and the lakeFS endpoints for Spark to be able to communicate to the lakeFS installation the same way it does with the S3, the actual S3. Now, so here I'm just creating some dummy data frame, and I will be writing it to the lakeFS repository smart data under the branch name. So let's see how it works. Okay, so I've created the files, and I can see that now I have in my uncommitted changes the Spark job output. I could also use the CTL and read those files and list those files. And here we go. Those are the files that we're reading. Now let's use lakeCTL and commit to this branch. And I'm committing to the branch name. Now let's say that I don't have any uncommitted changes, and I do have my first job output commit presented. Now back to the Spark notebook. I will try to read from the main branch, and it works. I see the data that was introduced into the main branch in the Smart Data repository. Now, let's use the lakeCTL tool to create another branch. So let's create branch create. Let's see the commands. smart data. I'm going to name this branch feature one branch, and the source of the branch is going to be the main branch, which is the only branch I currently have. And we have two branches list. Here we go. We see that we have two branches pointing to the same commit. That's because the feature one branch was just created from the main branch. Now let's create some more data, but this time pointed to the feature one branch inside the smart data repository, and use the mode override to replace the current files that we have inside the feature one branch. Okay, so this works. Back to the UI and see the uncommitted changes done to the feature one branch. As we can see with the override mode, then the previous files of the job were replaced by the second run of the job. And let's use this time commit changes from here. So second job output. And if we go to the commits of feature one, we could see that they were safely committed, but I haven't interacted with the main branch, and it is not impacted by the changes I've made to the feature one branch. Now let's simply read the data from the main branch and the feature one branch to see the difference between the two. This is where you could experiment with the data and compare the results before merging it back to master. Now let's use the XCTL one last time and merge. What are the commands? Source ref will be smart data feature one, and destination is going to be smart data main branch. And just like that, I see that 7 files were added and 4 were removed. If we go back to the UI and look at the commits of the main, we would see 2 new commits, the second job output that came from feature one branch, and the actual merge commit from feature one into main. So this was the demo. Let's go back to presenting. And that was all I had for today. Thank you for listening. You could go and use our quick start guide to easily install lakeFS locally. You could also check our docs and or join to our lakeFS Slack channel. We have some active community there. Or as an open source project, you could always contribute to it, or even just like starting the repo in GitHub. Thank you.
Thank you, Itai. We have a couple of questions in the chat. Yeah, so thank you for your talk. It was very nice to see actually working demo and how you show it. I can't
believe that it worked.
Yeah, it's always like a leap of faith, usually. Do you say that the lakeFS is generally complete project that you can use in production, or do you still feel like it's some sort of a beta version that you need to be careful about it? So how stable is it in your opinion?
It's a good question. It's been out there for over a year, and we see more and more production uses of it. We have dozens of lakeFS installations running. So I could honestly say that I think it suits a production use case, but there always might be a case that wasn't tested before. We see it working in high scale. So yes, it's safe to say that you could use that in production environment, but it's always safe to experiment before you try it on the first day in your production environment.
Yeah, so one of the questions in the chat from Alexei is how many gigabytes is it okay to handle with lakeFS, which is kind of related to what you were talking about. Speaking of high throughput.
So there are two aspects of it. Managing the size of the data lake, lakeFS scales as well as any object store because it doesn't store anything. It's just a layer that sits between your applications and the object store. Now, the server itself is stateless, and you could have many lakeFS servers running that you can talk to, and on top of Kubernetes having a service. So the throughput of lakeFS is also really high. And we haven't seen a case in production where lakeFS becomes the bottleneck. Not just yet. And I'm talking about throughput of gigabytes of data per second.
Cool. Yes, I hope it covers that. Another question from Marina is, does lakeFS work with Google Cloud Storage? I think you mentioned that it supports different, but can you elaborate on that?
Yes, it does. So it supports S3, and it supports Google Cloud Storage, and it supports the Azure Blob Storage, and also Minio if you want your personal S3 buckets that are detached from the S3. We are also planning on adding Oracle Cloud someday in the near future. So yeah, wherever our clients or our users go, we go there.
Yeah, cool. I don't have any questions from the chat. So if anyone is watching and would like to add a question, please speak up. Otherwise, I'd like to know that to continue that, is it universally supported? I assume that since it's an object store, you don't really have that much overhead, so it doesn't really matter what cloud provider you use, as long as it has an object storage, right?
Correct. So there's the part where you interact with lakeFS, which most applications, or let's say most cloud providers, when they write their object store, they support an S3 gateway. So basically, if you have your Spark job running some Google or Azure file systems or Hadoop file systems, they would interact with those cloud storages in a way that lakeFS know how to respond to as well. And the S3 gateway is a really powerful protocol because it was the first into market, and it made most applications and most other object storage aligned to it. So lakeFS supports that from day one.
That's great, but you repeatedly say that lakeFS don't really have any overhead. Is it technically true that you don't really store anything additional to the data, or is there any tiny overhead or something? Can you estimate how big is that?
So I talked about the data model. Each commit is represented by a single meta range file and a couple of dozens of range files, which every one of them is a few megabytes. It really depends on the size of your lake. But lakeFS uses a really small fraction. I'm talking about less than 0.1% of the size that your objects take. So when you store in S3, I think that a gigabyte of data costs you just a little more than 2 cents. So lakeFS overhead in terms of space is not significant. If we talk about the overhead when you are writing or reading through lakeFS, then it depends on how well you scale your lakeFS. But if the servers are not handling that much traffic simultaneously, then we're talking about a few milliseconds of overhead when you write through lakeFS and not directly to the object store. And allow me to add on top of that, we now have our lakeFS Hadoop file system, which basically just writes the metadata to lakeFS. So the data itself is written using our file system directly to your object store. And you simply, after that, simply tell lakeFS, hey, I've written this object in this lakeFS path to this location in your object store. Please make the metadata link. And you get the versioning without having to scale lakeFS because the data is not reading or written through lakeFS.
I see. Speaking of git-like experience, we have one more question from Igor. If we can access data in old commits, how you can control disk size of old version of objects, and the same for unmerged versions. So I assume if there is some tooling for housekeeping your data repository in that sense.
So I can think of one thing that is housekeeping, which is retention. Well, you want versioning, but you don't want your data to be in the lake forever. So we have retention capabilities. You could say that for these branches, I want the data and the metadata to be stored for 14 days, and for these branches for a year. It all depends on your use case. So this is one housekeeping that I can think of. I can also think about the life cycle of objects, like that are not committed, so they're not really part of any commit. And also, so we have some garbage collection that you can also define rules for, and it will like traverse your object store, your lakeFS repository, and delete those after a defined time. I hope that answers the question.
Yeah, please elaborate if it's not. But speaking of Git overall experience, we usually do use a lot of like Git tools like cherry pick and bisect and rebase and everything and stuff like that. Would you say that it's possible to do that in lakeFS, or is it something like planned in the future? How honest is this comparison that it's like Git-like experience?
So although we talk the same language, we can't really use Git under the hood in order to implement a versioning engine for data, because the scale is different and it works in remote, unlike Git where you have it locally and then you push changes. So we constantly add more and more features to lakeFS to be as paired with Git as we can. So I discussed the revert and the rollback capabilities. That was something that was not introduced out of the box. And as we hear more and more feature requests from our users, then we know how to prioritize those better. We keep hearing about cloning lakeFS repository, which is an option. Now you said cherry picking. All of these users' input help us to prioritize what features we would be working on next.
Okay, and how is that decided? Do you have like a, I don't know, Slack community where you vote on what's going to happen next, or is it just whatever you decide. It's fun.
So we have a Slack community. It's not really a democracy, but we keep in touch with our users. And when we hear something more than once, or even if we hear it a single time and we think that the use case is really valid and could help contribute and could help other users as well. So yeah, by all means, we prioritize it and go and work on it. It's not just the Git features, it's the different object stores and the different applications out there, like Hive Meta Store that we have a solution for, but maybe we are working to improve that solution. So yeah, we are in touch with the community, with our users, and we are rely on their inputs to prioritize our upcoming tasks.
Speaking of protection, how's I don't know if it's okay to talk about security in the sense that how secure everything is, because it basically boils down to the object store implementation, right?
So lakeFS, in order to run, it needs to have credentials to write and read from the object store. But to interact with lakeFS, it's a whole different set of authentication on authorization. So it is currently handled in lakeFS where you create your user. It's all RBox. So you create your users and you assign them to groups, and those groups could have different permissions like reading and writing from paths, but also branches and repositories. And so this is all handled by lakeFS. You could have your data scientist in the organization allowed to create just specific named branches, and no one is allowed to commit or merge directly into main. This kind of permissioning that lakeFS exposes. We are also working on integrating more third-party authentication solutions. The last one would be LDAP, and we're trying to support everything that is out there. Next in line is OAuth.
Yeah, I guess once you get that, you basically cover most of the use cases. So is there an option to do like a protected branches where you can merge only if someone else approves it or something, or like you have two approvals, stuff like that?
So approval is an issue that we have open, but we haven't implemented yet. But we do have the protected branch mechanism, which is you are not allowed to write or read from your production branch, for example, or commit to it at all. You can only do that while merging from a different branch. And while you do that, you could implement the right tools, the right hooks, the lakeFS hooks that will run arbitrary code or invoke some call to your server so that you can validate which changes are introduced into your production branches.
So for those, you need like it run by some part of lakeFS, the hooks itself, or is it a separate CI integration?
So the CI is invoked by lakeFS. We currently support two kinds of hooks. The first one is Airflow. You simply want to trigger some Airflow DAG after you merge to a branch, for example. And the second one is a custom HTTP request that is being sent to the server of your liking, and the operation would succeed if you return any 200, 204 response to lakeFS. So yes, for now, it is up to the data engineers, to the developer to spin up the server receiving those hooks and implement its own business logic to support the lakeFS hooks.
I see. And I assume every commit is also signed by like a signature of the user who committed it, right? And you can sort of check the PGP or something, right?
Yeah, we have all the metadata sent as part of the request.
Cool.
We also, I think we also provide some Flask server written in Python as an example of things you could do with hooks. So basically working on top of that, implementing your own business logic would be very simple. We have Terraforms for spinning lakeFS with its database and the hook server. So it's not part of lakeFS, but we do have some quick solutions for experimenting and building on top of.
Cool. Yeah, so I think that's about it for the talk. Thank you again for your time. We're not done yet. We will go to discussion room. I think you have the Zoom link and you will have the follow-up from other people who's supposed to help you with that. But yeah, see you there in a couple of minutes. And thanks again for your talk and your presentation. Thank you.
Thank you.